every second of your life you're hurtling through space at over 600 kilometers per second. Not just spinning with Earth, not just orbiting the Sun, but racing towards something so massive and so distant that astronomers didn't even know it existed until 1989. We call it the Shapley Supercluster, a collection of thousands of galaxies so enormous that its gravity reaches across 400 million light-years to tug at our Milky Way. Tonight we'll drift slowly through that cosmic mystery, from Edwin Hubble's first observations of galactic motion to the Planck satellite's precise measurements of our universe's hidden currents. The data whisper the same extraordinary message. Something unimaginably vast is pulling us through the darkness. Yet most people have never heard its name, and even fewer understand why this distant giant controls our cosmic destiny. Let your mind settle into this vastness. Allow yourself to feel that gentle, inexorable pull as we explore what's really moving our galaxy through space. Part 1. What if I told you that right now, as you sit reading these words, you're hurtling through the cosmos at an almost incomprehensible speed of 600 kilometers every single second? This isn't about Earth spinning on its axis or our planet orbiting the Sun, though those motions are happening too. This is about something far more extraordinary and mysterious. Our entire Milky Way galaxy, with its 400 billion stars, countless planets, nebulae, and everything we call home, is racing through space toward a destination that remained hidden from human eyes for most of our species' existence. Imagine trying to feel this motion in your daily life. You can't, of course, because everything around you moves together in this cosmic dance. But the evidence for this incredible journey lies written in the very fabric of space itself, in the faintest whispers of radiation that fill every corner of our universe. Scientists call this the cosmic, microwave background radiation, the afterglow of the Big Bang that created everything we know. When astronomers first measured this ancient light with exquisite precision, they discovered something startling. Instead of being perfectly uniform in all directions, this primordial glow shows a subtle but unmistakable pattern. One side of the sky appears slightly warmer, the other slightly cooler, creating what researchers term a dipole signature. This temperature difference, though incredibly small, reveals our galaxy's motion through space like cosmic breadcrumbs leading us toward an invisible gravitational giant. The discovery emerged gradually through decades of patient observation and technological advancement. Early radio telescopes in the 1970s detected hints of this asymmetry, but it wasn't until sophisticated satellite missions that the full picture became clear. The Cosmic Background Explorer satellite, followed by even more sensitive instruments, mapped this temperature variation across the entire sky with unprecedented accuracy. What they found challenged our understanding of cosmic architecture and revealed that our local neighborhood of space is far from peaceful and static. The numbers tell an incredible story. 600 kilometers per second translates to more than 2 million kilometers per hour, fast enough to cross the entire diameter of our galaxy in roughly 50 million years. This speed dwarfs anything we experience on Earth and even exceeds the escape velocity needed to break free from our galaxy's gravitational embrace entirely. Yet here we are, still bound within the Milky Way, still following this ancient trajectory that began long before our solar system even formed. But what force could possibly be powerful enough to set an entire galaxy in motion and maintain that movement for billions of years? The answer lies not in what we can see, but in what remains hidden from our view. Somewhere beyond the veil of our own galaxy's dust and stars, something massive lurks in the darkness, exerting a gravitational influence so profound that it shapes the motion of everything within hundreds of millions of light years. This cosmic puppet master remained invisible to early astronomers because it lies in the direction we call the zone of avoidance, where our galaxy's own material blocks our view of the distant universe. Like trying to see through a dense forest, astronomers had to develop new techniques and technologies to peer through this cosmic curtain. When they finally succeeded, what they discovered was a structure so vast and massive that it redefined our understanding of cosmic scale. The Great Attractor, as this region came to be known, represents just the beginning of our story. Beyond it lies something even more extraordinary, a gravitational colossus that makes even the Great Attractor seem small by comparison. This hidden giant, known as the Shapley Supercluster, contains thousands of galaxies, arranged in a cosmic web of unimaginable proportions. Its gravitational reach extends across distances so vast that light itself takes hundreds of millions of years to cross from one side to the other. The realization that we live within the influence of such a structure fundamentally changed how astronomers think about cosmic geography and our place within it. Every star you see in the night sky, every constellation that has guided human navigation for millennia, every planet in our solar system participates in this grand cosmic migration. We are all passengers on a journey that began before Earth existed and will continue long after our sun burns out. This motion connects us to the largest structures in the known universe, making us part of a story that spans from the smallest atoms to the grandest cosmic architectures. Tonight, as you prepare for rest, consider this remarkable fact about your existence. You're not simply residing on a planet orbiting a star in a galaxy floating through empty space. You are part of an active, dynamic cosmic ecosystem where gravitational forces stretch across impossible distances, where invisible giants shape the trajectories of entire galactic neighborhoods, and where the ancient echoes of creation still guide us toward destinations we are only beginning to understand. How do you solve a mystery when the primary suspect remains completely invisible, hidden behind an impenetrable cosmic curtain that blocks every attempt at direct observation? This extraordinary challenge has captivated astronomers for nearly a century, as they've struggled to identify the gravitational force responsible for dragging our entire galaxy through space at breathtaking speeds. The perpetrator of this cosmic crime lies concealed within what scientists call the zone of avoidance, a region where our own Milky Way's dense collection of stars, gas and dust creates an opaque barrier that obscures roughly 20% of the observable universe from our view. Imagine trying to investigate a burglary while wearing a blindfold that covers a fifth of your vision, and you begin to appreciate the magnitude of this astronomical detective work. The story begins in the 1930s with a brilliant astronomer named Shapley, who unknowingly captured the first photographic evidence of our cosmic culprit. Working with primitive equipment by today's standards, Shapley methodically photographed the southern sky from South Africa, painstakingly cataloguing tens of thousands of galaxies on glass photographic plates. Among these images, he noticed an unusual concentration of galaxies in the constellation Centaurus, but the technology of his era couldn't reveal the true significance of this discovery. For decades afterward, this cosmic giant remained hidden in plain sight, waiting for astronomical technology to advance enough to unmask its true nature and overwhelming influence. The breakthrough came in the 1980s when a team of 7 astronomers, dubbed the Seven Samurai, developed sophisticated techniques for measuring galaxy distances with unprecedented precision. They discovered that hundreds of galaxies in our cosmic neighborhood were all streaming in the same direction, following invisible currents that pointed toward the same mysterious region Shapley had photographed 50 years earlier. These cosmic flows revealed the presence of something massive lurking behind the galactic veil, something with gravitational influence extending across hundreds of millions of light years. But seeing this hidden giant required more than optical telescopes could provide. Astronomers had to become cosmic archaeologists, using every wavelength of electromagnetic radiation to piece together clues about the invisible architecture shaping our universe. Radio waves penetrate cosmic dust more effectively than visible light, revealing hidden galaxy clusters and their associated magnetic fields. Infrared observations detect the heat signatures of distant stellar populations obscured by intervening material. X-ray telescopes reveal the superhot gas that permeates massive galaxy clusters, creating ghostly images of gravitational wells invisible to human eyes. Each new observational technique added pieces to an increasingly complex puzzle, slowly revealing the outline of something unprecedented in its scale and influence. The detective story deepened when astronomers realized that the initial suspect, the Great Attractor, was merely an accomplice in a much larger cosmic conspiracy. Behind this regional gravitational influence lay something even more massive and distant, a structure so vast that it dwarfs even the largest galaxy clusters by factors of thousands. This true mastermind, eventually identified as the Shapley Supercluster, contains more galaxies than astronomers can easily count, with a combined mass exceeding 10 million billion times that of our Sun. Its gravitational reach extends so far that its influences the motion of structures located hundreds of millions of light years away, including our own galactic neighborhood. Modern space telescopes have revolutionized our ability to peer through the cosmic fog that concealed this giant for so long. Sophisticated computer simulations help astronomers understand how gravitational forces propagate across such vast distances, creating the cosmic web of filaments and voids that organizes matter on the largest scales. Advanced surveys catalogue the positions and motions of millions of galaxies, revealing the subtle patterns in their collective behavior that betray the presence of hidden gravitational influences. Each technological advance brings us closer to understanding the full scope of the cosmic forces that govern our galaxy's motion through space. The investigation has revealed that our cosmic detective story involves not just one massive structure, but an entire hierarchy of gravitational influences operating on different scales. Local galaxy groups affect nearby galactic motions, regional superclusters create intermediate-scale flows, and the largest structures in the universe establish the broad currents that carry everything else along their predetermined paths. Understanding this cosmic hierarchy requires combining observations across multiple wavelengths, computer modeling of gravitational dynamics, and theoretical frameworks that can accommodate the mind-bending scales involved in these cosmic interactions. Tonight, as you contemplate this ongoing investigation, consider how human ingenuity has gradually unveiled one of the universe's greatest mysteries through patient observation and technological innovation, revealing the invisible giant that shapes our cosmic destiny. What if the entire universe carries within it a perfect fossil record of its own birth? A faint whisper of creation that fills every cubic centimetre of space with ancient light from the dawn of time itself. This remarkable phenomenon exists all around us at this very moment, invisible to our eyes yet detectable by sensitive instruments capable of measuring the universe's most subtle secrets. Scientists call this primordial glow the cosmic microwave background radiation, and its discovery represents one of the most profound achievements in modern astronomy. Born approximately 380,000 years after the Big Bang, when the universe had cooled sufficiently for atoms to form and space became transparent for the first time, this radiation has been travelling through the cosmos ever since, carrying within its electromagnetic signature the blueprint of cosmic structure and the keys to understanding our galaxy's mysterious journey through space. The cosmic microwave background pervades everything, passing through your body billions of times each second without your awareness. Yet this ancient light holds information about the universe's earliest moments and our current motion through the cosmic web. When astronomers first detected this radiation in the 1960s, they initially observed what appeared to be perfect uniformity in all directions, suggesting that the early universe possessed remarkable homogeneity. The temperature of this background radiation measures precisely 2.725 Kelvin above absolute zero, creating a nearly perfect black body spectrum that matches theoretical predictions with extraordinary accuracy. This uniformity initially puzzled scientists because it implied that regions of space separated by vast distances somehow maintained identical temperatures despite having no causal connection during the universe's infancy. However, as measurement techniques became increasingly sophisticated, astronomers began detecting tiny variations in this cosmic background that would revolutionize our understanding of both cosmic evolution and our galaxy's place within the universal framework. The breakthrough came when scientists realized that one particular pattern stood out, dramatically against the otherwise uniform cosmic glow. Instead of complete isotropy, the cosmic microwave background exhibits a distinctive dipole pattern, meaning that radiation arriving from one hemisphere of the sky appears systematically hotter, while the opposite hemisphere appears cooler. This temperature difference amounts to only a few thousandths of a degree, requiring extraordinary precision to detect, yet its implications are profound beyond imagination. The hot spot appears in the direction of the constellation Leo, while the cold spot lies in the opposite direction toward Aquarius, creating a cosmic compass that reveals our motion through the universe itself. This dipole pattern arises from a phenomenon called the Doppler effect, the same principle that causes ambulance sirens to change pitch as they approach and recede. As our galaxy moves through space, we encounter cosmic microwave background photons more frequently from the direction we're heading toward, causing that radiation to appear slightly blue-shifted and therefore hotter. Simultaneously, photons from behind us appear redshifted and cooler because we're moving away from their source regions. The magnitude of this temperature asymmetry directly measures our velocity relative to the cosmic rest frame, providing astronomers with a cosmic speedometer of unprecedented accuracy. Calculating our motion from this dipole signature requires accounting for multiple layers of movement that compound together like nested wheels within wheels. Earth orbits the Sun at 30 kilometres per second. The Sun orbits the galactic centre at approximately 220 kilometres per second, and our entire galaxy participates in the local group's gravitational dance at speeds approaching 100 kilometres per second. When astronomers carefully subtract all these known motions from the observed dipole pattern, they discover that our local group of galaxies moves at 627 kilometres per second relative to the cosmic microwave background frame of reference. This residual motion cannot be explained by any local gravitational influences, and therefore must result from the gravitational attraction of much more distant and massive structures. The discovery of our cosmic motion through microwave background observations opened an entirely new field of astronomical investigation focused on mapping large-scale cosmic flows and understanding the gravitational architecture that creates them. Subsequent missions have refined these measurements with increasing precision, revealing not only our overall motion, but also subtle variations in the cosmic background that trace the seeds of cosmic structure formation. These temperature fluctuations, typically measuring only a few millionths of a degree, represent the primordial density variations that eventually grew under gravitational amplification to become the galaxies, clusters, and superclusters we observe today. The cosmic's microwave background thus serves simultaneously as both a window into the universe's infancy and a detector for our current motion through space, connecting the smallest observable temperature differences with the largest gravitational structures in existence. How can an entire galaxy achieve velocities so extreme that they challenge our fundamental understanding of cosmic mechanics and gravitational physics? The answer lies within measurements so precise they reveal motion occurring at 600 kilometers every single second, a speed that defies easy comprehension and demands explanation through forces operating on scales previously unimaginable to human science. To appreciate the magnitude of this velocity, consider that our galaxy measures approximately 100,000 light-years across, containing hundreds of billions of stars arranged in spiral arms that sweep through space like cosmic pinwheels. At our current rate of motion, the entire Milky Way would traverse its own diameter in merely 50 million years, a time span that represents less than 1% of our galaxy's total age. This astounding speed exceeds the escape velocity needed for individual stars to break free from galactic gravity entirely, yet somehow our galaxy maintains its structural integrity while racing toward a destination that remained mysterious for decades after its discovery. Scientists refer to this phenomenon as peculiar velocity, distinguishing it from the uniform expansion that carries all cosmic structures away from each other as space itself stretches and grows. Hubble expansion creates predictable recession velocities that increase proportionally with distance, causing distant galaxies to appear to flee from us at speeds determined solely by their separation and the universe's expansion rate. However, peculiar velocities represent deviations from this smooth flow, indicating that additional gravitational influences modify the expected motion patterns. These gravitational perturbations arise from the uneven distribution of matter throughout space, creating regions of enhanced density that attract surrounding material while leaving voids that exert comparatively little influence on nearby structures. Measuring peculiar velocities requires extraordinary precision, because astronomers must first account for cosmic expansion before detecting the subtle additional motions caused by gravitational attraction. The process involves determining both the distance and recession velocity of galaxies, then comparing observed values with predictions based on smooth universal expansion. Any systematic deviations reveal the presence of gravitational influences beyond those expected from uniform matter distribution. In our case, the 600 km per second motion represents such a large deviation that it indicates the presence of gravitational sources with masses comparable to thousands of typical galaxy clusters concentrated within a relatively small cosmic volume. The discovery of this extreme motion immediately raised profound questions about cosmic architecture and the distribution of matter on the largest observable scales. Normal galaxy clusters contain sufficient mass to influence the motion of nearby galaxies within distances of several million light-years, but our observed velocity suggests gravitational influences extending across hundreds of millions of light-years. Such long-range attraction requires mass concentrations vastly exceeding anything previously catalogued by astronomical surveys, implying the existence of cosmic structures whose scale dwarfs conventional understanding of galactic organization and clustering. The implications extend beyond simple curiosity about cosmic geography because peculiar velocities provide direct measurements of gravitational fields and therefore the underlying matter distribution that creates them. Unlike electromagnetic observations that detect only luminous material, velocity measurements respond to all forms of matter, including the dark matter that comprises roughly 85% of cosmic mass, but emits no detectable radiation. Peculiar velocity surveys thus offer unique insights into cosmic structure formation and the invisible scaffolding that supports the visible universe we observe through traditional astronomical techniques. Understanding the source of our galaxy's extreme motion became a central challenge for cosmology because it suggested that cosmic structure extends to scales much larger than previously suspected. The 600 km/s velocity implies that our local group participates in gravitational flows involving millions of galaxies distributed across distances comparable to significant fractions of the observable universe. These flows represent the largest coherent motions detected in nature, connecting our immediate cosmic neighborhood with structures so distant that their light requires hundreds of millions of years to reach us. The search for the gravitational source responsible for this motion led astronomers to develop increasingly sophisticated mapping techniques capable of detecting matter concentrations hidden behind intervening cosmic material. Radio astronomy revealed galaxy populations invisible to optical telescopes. Infrared surveys penetrated cosmic dust clouds that obscure distant structures, and X-ray observations detected hot gas associated with massive galaxy clusters. Each new observational technique added pieces to an emerging picture of cosmic organization that operates on scales vastly exceeding early theoretical predictions and challenges fundamental assumptions about the maximum size of gravitationally bound or influenced structures. The mystery deepened when astronomers realized that accounting for all known nearby mass concentrations still fails to explain the full magnitude of our observed motion, suggesting that even more distant and massive structures contribute to the gravitational field shaping our cosmic trajectory through space. Why would thousands of galaxies scattered across hundreds of millions of light-years all participate in the same cosmic dance, streaming together like leaves caught in an invisible river current, flowing through the darkness of space? This extraordinary question began haunting astronomers in the 1970s as they developed revolutionary techniques for measuring galaxy distances and velocities with unprecedented accuracy. The breakthrough came through systematic studies of galaxy redshifts, the stretching of light wavelengths that occurs when objects move away from observers due to cosmic expansion. By combining redshift measurements with independent distance estimates derived from stellar brightness indicators, astronomers could separate the effects of universal expansion from local gravitational influences, revealing the subtle but persistent deviations that betray the presence of massive, hidden structures. The pioneering work required painstaking observations of individual galaxies using the largest available telescopes, often spending entire nights collecting enough photons to measure precise velocities for single distant objects. Early surveys focused on relatively nearby galaxies where distance measurements remained reliable, gradually expanding their scope as observational techniques improved and theoretical understanding deepened. Each new galaxy added to these catalogues provided another data point in an emerging map of cosmic motion that would eventually revolutionize our understanding of large-scale structure and gravitational dynamics. The pattern that emerged from these systematic observations proved both surprising and deeply puzzling to the astronomical community. Rather than random motions in all directions, as might be expected from purely local gravitational influences, the data revealed coherent streaming patterns extending across vast regions of space. Hundreds of galaxies within our cosmic neighborhood appeared to move in coordinated fashion, all following similar trajectories through space despite being separated by distances so large that gravitational communication between them should require hundreds of millions of years. This coherent motion suggested the presence of a unified gravitational influence operating on scales previously unimaginable, challenging existing models of cosmic structure formation and evolution. The direction of this mysterious flow became increasingly clear as more galaxies were added to velocity catalogues and statistical analysis techniques grew more sophisticated. Mathematical methods borrowed from fluid dynamics revealed that galaxies throughout our local volume of space stream toward a specific region in the southern celestial sphere, concentrated in the direction of the constellation Centaurus near its border, with Triangulum Australis and Norma. This convergence point lies frustratingly close to the plane of our own galaxy, placing it within the zone of avoidance where dust and stellar populations obscure our view of distant cosmic structures. The challenge of studying this hidden region required developing new observational strategies and exploiting wavelengths of electromagnetic radiation capable of penetrating the intervening galactic material. Radio astronomy proved particularly valuable because radio waves travel through cosmic dust with minimal absorption, revealing galaxy populations completely invisible to optical surveys. Infrared observations detected thermal emission from stellar populations hidden behind dust clouds, while X-ray telescopes revealed the hot gas signatures associated with massive galaxy clusters. Each wavelength provided complementary information about the structures responsible for the observed gravitational influence, gradually building a picture of cosmic architecture that exceeded all previous expectations for scale and complexity. The term Great Attractor emerged from this body of observational work as astronomers struggled to characterize the gravitational source responsible for such widespread and coherent motion patterns. Unlike conventional galaxy clusters that create localized gravitational wells affecting only nearby neighbors, the Great Attractor appeared to influence structures across distances spanning significant fractions of the observable universe. Its gravitational reach extends far beyond anything previously catalogued, suggesting mass concentrations comparable to thousands of typical galaxy clusters distributed across regions hundreds of millions of light-years in extent. This implied the existence of cosmic structures operating on scales that approach theoretical limits for gravitationally bound systems within an expanding universe dominated by dark energy. Mapping these cosmic flows required international collaboration between observatories scattered across multiple continents, each contributing specialized capabilities to the growing database of galaxy positions and velocities. Southern Hemisphere telescopes provided crucial access to the Centaurus region, where the flow convergence appeared most concentrated, while northern facilities expanded coverage to trace the full extent of participating structures. Computer algorithms processed increasingly large datasets to identify subtle correlation patterns that human analysis might miss, revealing the fingerprints of gravitational influence extending to greater distances than any individual survey could encompass. The discovery of coherent cosmic flows represented a fundamental shift in understanding cosmic organization, revealing that gravitational structures exist on scales intermediate between individual galaxy clusters and the universe as a whole, operating as bridges that connect local galactic neighborhoods with the largest architectural elements in cosmic structure formation. Could a single determined scientist armed with nothing more than photographic plates and unwavering patience accidentally stumble upon one of the most colossal structures in the entire observable cosmos? This remarkable tale begins in 1930 when Harlow Shapley, already renowned for revolutionizing our understanding of galactic dimensions, embarked upon an ambitious project that would forever change humanity's perspective on cosmic architecture. Fresh from his groundbreaking work measuring the true size of our Milky Way through globular cluster studies, Shapley possessed both the vision and tenacity required for unprecedented astronomical undertakings. His latest endeavour involved systematically photographing vast regions of southern skies, using the 24-inch Bruce telescope stationed at Bloemfontein Station in South Africa, a location chosen specifically for its exceptional atmospheric clarity and unique vantage point of celestial territories, invisible from Northern Hemisphere observatories. Working with primitive equipment by contemporary standards yet revolutionary for its era, Shapley methodically exposed glass photographic plates night after night, capturing faint smudges of light that represented entire galactic systems containing billions of individual stars. Each exposure required careful planning and precise timing to maximize the collection of photons from incredibly distant sources, often necessitating hours of patient waiting as a mechanical clockwork drives slowly tracked celestial objects across their apparent paths through darkness. The photographic process itself demanded meticulous attention to chemical development techniques, temperature control, and contamination prevention, as even minor errors could render weeks of observational work completely useless. Shapley's ultimate objective transcended mere cataloguing of randomly distributed cosmic objects. He he envisioned creating the first comprehensive map of galactic distribution across significant portions of the universe, hoping to discern patterns or structures that might reveal fundamental principles governing cosmic organization. His systematic approach involved dividing the accessible sky into manageable sectors, methodically photographing each region multiple times under varying atmospheric conditions to ensure complete coverage and reliable detection of the faintest possible galactic sources. The scope of this undertaking boggled contemporary imaginations as Shapley aimed to document 76,000 individual galaxies, each representing a complete stellar system, comparable to our own Milky Way in complexity and content. This numerical target reflected not arbitrary ambition, but careful calculation based on estimated galactic densities and the survey's planned coverage area, suggesting that Shapley possessed remarkable foresight regarding cosmic structure and organization decades before modern theoretical frameworks emerged. Working largely alone with minimal institutional support, Shapley demonstrated extraordinary dedication to scientific discovery, spending countless nights in the isolated South African observatory, meticulously adjusting telescope settings, changing photographic plates, and recording observational conditions in detailed logbooks that would later prove invaluable for interpreting his results. The physical challenges of this work cannot be overstated. Maintaining focus and precision during long cold nights while operating delicate mechanical equipment required both physical endurance and mental discipline rarely demanded in other scientific pursuits. Beyond technical obstacles, Shapley faced the intellectual challenge of developing entirely new methods for analysing photographic data, as no precedent existed for processing such vast quantities of galactic position information. He pioneered techniques for measuring galactic brightnesses, estimating distances, and identifying clustering patterns that would later become standard astronomical procedures still employed by modern researchers using sophisticated digital instruments. Perhaps most remarkably, Shapley possessed no inkling that his systematic survey would capture evidence of gravitational influences operating across distances so vast they challenged fundamental assumptions about cosmic structure formation and evolution. The photographic plates accumulating in his South African darkroom contained hidden within their emulsion layers the first recorded images of what would eventually be recognized as among the largest gravitationally influenced structures in the known universe. Working by lamplight in makeshift laboratory conditions, Shapley painstakingly examined each plate through magnifying equipment, marking galactic positions and estimating relative brightnesses, using visual comparison techniques that required both trained expertise and artistic sensitivity. His detailed records documented not merely galactic positions, but also morphological characteristics, clustering tendencies, and apparent magnitude distributions that would prove crucial for later theoretical interpretations. The methodical nature of Shapley's work established scientific standards for systematic sky surveys that continue influencing modern astronomical practices, demonstrating how careful observational discipline can yield discoveries far beyond original research objectives. Unbeknownst to Shapley, embedded within his growing catalogue of galactic positions lay evidence for cosmic architecture operating on scales that wouldn't be fully appreciated until technological advances permitted detailed velocity measurements and three-dimensional mapping techniques decades later. What happens when an experienced astronomer suddenly encounters something on photographic plates that fundamentally challenges everything previously understood about cosmic distribution and galactic arrangement? In 1932, while meticulously examining his accumulated collection of glass plates in the cramped South African Observatory, Harlow Shapley made an observation that would haunt astronomical thinking for decades to come. Among the thousands of faint stellar systems scattered across his photographic survey, one particular region in the constellation Centaurus displayed characteristics so unusual and pronounced that it demanded immediate attention and careful analysis. Rather than the relatively random distribution of galaxies expected from uniform cosmic matter density, this specific area revealed an unmistakable concentration of galactic objects arranged in patterns that defied conventional explanations. Shapley's trained eye, honed by years of analysing stellar distributions and globular cluster arrangements, immediately recognized that this clustering represented something entirely different from typical galactic neighborhoods or even the richest known galaxy groups. The structure possessed what Shapley described as great linear dimension, suggesting elongated architecture stretching across significant angular distances on the sky. its numerous population exceeded anything previously catalogued in systematic surveys, indicating mass concentrations far beyond normal clustering expectations. Most intriguingly, the arrangement exhibited distinctly elongated form, hinting at underlying organisational principles operating on scales previously unimaginable in astronomical context. These observations mark the first human recognition of what would eventually be identified as one of the most massive gravitationally bound structures in the observable universe, though Shapley himself couldn't possibly appreciate the full implications of his discovery given the limited theoretical frameworks available during the 1930s. Working with nothing more than visual inspection techniques and basic photographic photometry, Shapley attempted to estimate the distance to this remarkable concentration using the best available methods of his era. He compared the apparent sizes and brightnesses of galaxies within the Centaurus cloud to similar objects in better understood regions, particularly the Virgo cluster, which represented the nearest substantial galactic grouping known at the time. Through careful analysis of average galactic diameters and brightness characteristics, Shapley calculated that his mysterious Centaurus concentration lay approximately 14 times farther away than the Virgo system, placing it at enormous distances that tested the limits of contemporary cosmological thinking. Modern measurements using sophisticated techniques unavailable to Shapley have confirmed his distance estimate with remarkable accuracy, demonstrating the power of careful observational analysis even when conducted with primitive instrumentation. His calculation placed the Centaurus structure at roughly 231 megaparsecs from Earth, a distance so vast that light requires over 700 million years to traverse the intervening space. This extraordinary accuracy in distance estimation, achieved through purely photographic methods, showcases Shapley's exceptional skill in astronomical observation and analysis, establishing him as one of history's most capable practitioners of classical positional astronomy. The elongated morphology that captured Shapley's attention reflects the true three-dimensional architecture of what modern astronomers recognize as a supercluster filament, a cosmic web structure where galaxies align along preferred directions determined by gravitational dynamics and dark matter distribution patterns. These filamentary arrangements represent some of the largest coherent structures in the universe, stretching across hundreds of millions of light-years and containing thousands of individual galaxy systems bound together by mutual gravitational attraction. Shapley's description of the structure's linear characteristics provided the first observational evidence for cosmic web architecture, though theoretical understanding of such large-scale organization wouldn't develop until decades later, when computer simulations revealed how gravitational instability creates filamentary patterns from initially smooth matter distributions. The numerous population that impressed Shapley reflects the extraordinary richness of this particular cosmic region, which contains galaxy densities far exceeding average universal values. Modern surveys have catalogued over 8,000 individual galaxies within this supercluster complex, representing a mass concentration equivalent to tens of millions of billion solar masses distributed across a volume comparable to significant fractions of the observable universe's total extent. Shapley's recognition of this population density anomaly demonstrated his remarkable ability to detect statistical deviations in galactic distributions using only visual examination of photographic plates, a skill requiring both mathematical intuition and extensive experience with cosmic object catalogues. Perhaps most significantly, Shapley's careful documentation of his observations established a permanent scientific record that would prove invaluable when later generations of astronomers developed the theoretical frameworks and technological capabilities necessary to fully understand the implications of his discovery. His detailed notes describing the elongated morphology, exceptional richness, and estimated distance provided crucial baseline information that guided subsequent investigations and confirmed the reality of large-scale structure, long before modern cosmological models predicted such arrangements should exist. How could one of the most important astronomical discoveries in human history become buried beneath decades of scientific neglect, forgotten like ancient treasure hidden in dusty archives? After Shapley published his remarkable findings about the extraordinary galactic concentration in Centaurus, the broader astronomical community remained largely indifferent to the implications of his work, focusing instead on more immediately accessible research problems that promised quicker results with existing technological capabilities. The 1930s marked a period of rapid advancement in stellar physics and galactic structure studies, with astronomers captivated by revolutionary discoveries about nuclear fusion processes powering stars, the expanding universe revealed through Hubble's redshift observations, and the detailed mapping of our own Milky Way's spiral architecture. These compelling research frontiers demanded immediate attention and offered tangible progress using available instrumentation, while Shapley's distant galactic assemblage seemed impossibly remote and difficult to investigate further with contemporary methods. The scientific community's attention naturally gravitated towards problems that could be solved with existing telescope capabilities and theoretical frameworks, leaving Shapley's Centaurus cloud as an intriguing but seemingly inaccessible curiosity relegated to specialized astronomical catalogues. For 5 full decades following Shapley's initial publication, this cosmic leviathan remained essentially invisible to active astronomical research, mentioned occasionally in comprehensive surveys, but never subjected to the detailed investigation that would reveal its true significance for cosmological understanding. The intervening years witnessed tremendous advances in observational astronomy, including the development of electronic detectors, sophisticated photographic techniques, radio telescopes capable of penetrating cosmic dust, and theoretical breakthroughs in understanding galactic evolution and clustering phenomena. Yet despite these technological improvements, the Shapley concentration continued to elude systematic study because its extreme distance placed it beyond the effective reach of most astronomical instruments and techniques available before the computer age. Early radio surveys detected tantalizing hints of unusual activity in the Centaurus region, but lacked the sensitivity and resolution necessary to map individual galactic components or measure the velocities required for understanding gravitational dynamics. Optical telescopes could photograph the brightest galactic members, but couldn't penetrate the zone of avoidance sufficiently to reveal the structure's full extent or appreciate its connection to larger cosmic architecture. The primary obstacle preventing rediscovery involved not merely technological limitations, but also conceptual barriers within astronomical thinking during the mid-20th century. Most astronomers assumed that galactic clustering occurred only on relatively modest scales, with the largest known structures being individual galaxy clusters containing perhaps hundreds of member galaxies distributed across a few million light-years. The possibility that gravitational organization might extend to scales hundreds of times larger seemed theoretically implausible, given contemporary understanding of cosmic expansion and structure formation processes. Einstein's general relativity provided the mathematical framework for understanding gravitational dynamics, but the computational tools necessary for modeling large-scale structure evolution wouldn't emerge until electronic computers became available for scientific applications during the 1960s and 70s. Without theoretical guidance suggesting that structures like Shapley's concentration should exist, observers had little motivation to develop the specialized techniques required for their systematic investigation. The situation changed dramatically when new observational capabilities converged with evolving theoretical perspectives during the late 20th century. Advances in electronic detector technology enabled precise measurement of galactic velocities across much greater distances than previously possible, while computer simulations began revealing how small initial density fluctuations could grow through gravitational amplification to create hierarchical clustering patterns extending to enormous scales. These theoretical developments predicted that the universe should contain structures intermediate between individual galaxy clusters and the cosmic web itself, providing intellectual motivation for renewed searches for exactly the type of large-scale organization that Shapley had glimpsed decades earlier. Radio astronomy finally matured to the point where systematic surveys could map galactic populations hidden behind our own galaxy's obscuring material, while infrared observations began revealing thermal signatures from stellar populations invisible to optical telescopes. X-ray astronomy detected hot gas associated with massive galaxy clusters, providing independent evidence for gravitational wells capable of binding thousands of individual galactic systems across vast distances. Most crucially, systematic redshift surveys began accumulating velocity measurements for thousands of galaxies distributed throughout local cosmic volumes, enabling three-dimensional mapping of galactic motions and revealing the coherent streaming patterns that would eventually lead astronomers back to Shapley's forgotten discovery. The convergence of these technological capabilities with emerging theoretical frameworks for large-scale structure formation created the intellectual climate necessary for appreciating the true significance of observations that had been overlooked for half a century, setting the stage for one of astronomy's most remarkable rediscoveries. What drives 7 dedicated scientists to embark upon an astronomical quest so ambitious that it would fundamentally reshape humanity's understanding of cosmic architecture and galactic motion? During the 1980s, an extraordinary collaboration emerged between researchers scattered across multiple institutions, united by their shared determination to solve one of astronomy's most perplexing mysteries regarding the peculiar velocities observed throughout our local cosmic neighbourhood. This legendary team, playfully dubbed the Seven Samurai by their colleagues in recognition of their fierce dedication and coordinated approach to tackling seemingly impossible observational challenges, consisted of Alan Dressler from Carnegie Observatories, Sandra Faber from University of California, Santa Cruz, David Burstein from Arizona State University, Roger Davies from Oxford University, Donald Lyndon Bell from Cambridge University, Roberto Turlevich from Royal Greenwich Observatory, and Gary Wegner from Dartmouth College. Each member brought specialised expertise in different astronomical techniques and theoretical perspectives, creating a formidable intellectual consortium capable of addressing problems that had frustrated individual researchers for decades. Their revolutionary approach centered on developing unprecedented precision in measuring galactic distances using Cepheid variable stars as standard candles, a technique pioneered by Henrietta Leavitt earlier in the century, but never before applied systematically to such large samples of distant galaxies. Cepheid variables possess the remarkable property that their intrinsic brightness correlates directly with their pulsation periods, allowing astronomers to determine absolute luminosity by simply timing the regular cycles of brightening and dimming exhibited by these stellar beacons. By comparing known intrinsic brightness with observed apparent magnitude, researchers can calculate precise distances to host galaxies, providing the crucial baseline measurements necessary for detecting peculiar velocities that deviate from smooth cosmic expansion. The Seven Samurai systematically targeted 400 galaxies distributed throughout accessible regions of a local cosmic volume, spending countless nights at premier observatories collecting the high-quality photometric and spectroscopic data required for reliable distance and velocity determinations. This comprehensive survey demanded extraordinary patience and meticulous attention to observational detail, as each galactic measurement required multiple telescope sessions conducted under optimal atmospheric conditions to achieve the precision necessary for detecting subtle velocity deviations. The team pioneered innovative data reduction techniques and statistical analysis methods, specifically designed to extract meaningful patterns from large astronomical datasets, establishing protocols that would become standard practice for subsequent large-scale structure investigations. Their systematic approach yielded the first detailed 3-dimensional map of galactic motions extending across significant cosmic volumes, revealing coherent streaming patterns that had remained invisible to smaller-scale studies conducted by individual research groups. The breakthrough moment arrived when statistical analysis revealed unmistakable evidence for coordinated motion among hundreds of galaxies scattered across vast distances, all flowing toward a common convergence point located somewhere beyond the observable boundaries of their survey volume. This coherent streaming behavior could not be explained by random gravitational interactions between neighboring galactic systems, instead requiring the presence of a massive attracting source operating on scales previously unimaginable in astronomical context. Mathematical modelling indicated that producing such widespread and organised motion patterns would necessitate gravitational influences equivalent to tens of thousands of typical galaxy clusters concentrated within a relatively compact cosmic region. The Seven Samurai faced the challenging task of characterizing this invisible gravitational source based solely on its dynamical effects observed in galactic velocity measurements, developing sophisticated theoretical frameworks for inferring mass distributions from observed motion patterns. Their calculations suggested that the mysterious attracting region possessed total mass exceeding 10 to the 16th power solar masses, making it comparable to the largest known cosmic structures while remaining completely hidden from direct optical observation. The team's careful analysis pinpointed the approximate location of maximum gravitational influence towards specific celestial coordinates lying frustratingly close to our galaxy's equatorial plane, where dense concentrations of stars and interstellar material create an opaque barrier preventing direct telescopic investigation. Recognizing the need for a memorable designation for their revolutionary discovery, the Seven Samurai introduced the evocative term Great Attractor, to describe this enigmatic gravitational focal point that seemed capable of influencing galactic motions across unprecedented distances. This nomenclature captured both the scientific precision of their measurements and the sense of wonder inspired by detecting cosmic architecture operating on scales that challenged fundamental assumptions about gravitational organization in the universe, establishing a legacy that continues inspiring astronomical research into large-scale structure formation and evolution. How can astronomers study something that lies completely hidden behind an impenetrable cosmic curtain that blocks their view as effectively as a brick wall obscures distant landscapes? The answer to this frustrating challenge involves understanding one of observational astronomy's greatest obstacles, a region that astronomers have reluctantly named the zone of avoidance, where our own Milky Way galaxy creates an opaque barrier preventing direct observation of roughly 20% of the entire celestial sphere. This cosmic blind spot arises from the unfortunate geometric reality that Earth sits embedded within our galaxies, flattened disk structure, surrounded by vast clouds of interstellar dust, countless billions of foreground stars, and dense molecular gas concentrations that absorb, scatter, and reflect electromagnetic radiation from more distant sources. The situation resembles attempting to navigate through a fierce sandstorm, where swirling particles completely obscure visibility beyond a few meters, except in this case the obscuring material extends across thousands of light years, and the targets of interest lie hundreds of millions of light years beyond our local galactic environment. Traditional optical telescopes prove virtually useless for penetrating this cosmic fog, as visible light photons encounter overwhelming interference from intervening stellar populations and dust particles that effectively eliminate any hope of detecting faint background galaxies or measuring their properties through conventional photographic techniques. The obstruction creates a fundamental paradox because the great attractor's location coincides precisely with the densest portions of this observational dead zone, placing the most important gravitational structure in our cosmic neighborhood tantalizingly beyond the reach of direct investigation using standard astronomical methods. Early attempts to peer through galactic material using increasingly powerful optical instruments yielded only frustration, as even the most sophisticated telescopes equipped with advanced photographic emulsions and sophisticated optical filters failed to reveal meaningful details about structures lurking behind the cosmic veil. The breakthrough required abandoning traditional approaches entirely and embracing revolutionary observational techniques that exploit different regions of the electromagnetic spectrum where galactic material proves less opaque to penetrating radiation. Radio astronomy emerged as the first successful method for circumventing the zone of avoidance limitations because radio waves possess much longer wavelengths than visible light and therefore interact differently with the interstellar dust particles. While microscopic dust grains efficiently absorb and scatter optical photons, they present minimal obstacles to radio frequency radiation, allowing radio telescopes to detect distant galaxies and to map their distributions even when optical observations yield only blank darkness. Pioneer radio surveys conducted during the 1970s and 80s began revealing previously unknown galaxy populations hidden behind our galactic disk, providing the first tentative glimpses of cosmic structures that had remained completely invisible to decades of optical astronomy. Infrared observations offered another powerful tool for penetrating galactic obscuration, as thermal radiation from stellar populations in distant galaxies can traverse dusty regions more effectively than shorter wavelength optical light. Sophisticated infrared detectors cooled to extremely low temperatures proved capable of detecting heat signatures from galaxy clusters and superclusters located within the zone of avoidance, gradually building a picture of hidden cosmic architecture through patient accumulation of thermal measurements. These infrared surveys revealed the presence of massive galaxy concentrations exactly where theoretical predictions suggested the great attractor should reside, providing crucial confirmation that substantial gravitational sources indeed existed within the observationally challenging region identified by peculiar velocity studies. X-ray astronomy contributed yet another perspective on hidden cosmic structures by detecting the superheated gas that pervades massive galaxy clusters and superclusters. This intergalactic medium reaches temperatures of millions of degrees due to gravitational compression and shock heating processes, causing it to emit characteristic X-ray signatures that penetrate galactic obscuration far more effectively than optical radiation. Space-based X-ray telescopes equipped with sensitive detectors began mapping hot gas distributions throughout the zone of avoidance, revealing the locations and approximate masses of galaxy clusters that remained completely invisible to ground-based optical surveys. The combination of radio, infrared, and X-ray observations gradually assembled a comprehensive picture of cosmic structures hidden behind our galactic disk, demonstrating that the Great Attractor region indeed contains the massive concentrations of galaxies and hot gas required to explain the gravitational influences detected through peculiar velocity measurements, though complete understanding would require even more sophisticated observational campaigns and theoretical modelling efforts. What happens when cutting-edge astronomical technology finally pierces the cosmic veil, only to discover that reality proves far stranger and more complex than anyone anticipated? The breakthrough observations using X-ray space telescopes revealed spectacular phenomena hidden within the Great Attractor region, as sophisticated instruments detected vast clouds of superheated plasma reaching temperatures exceeding 50 million degrees Celsius, glowing brilliantly in high-energy radiation completely invisible to human eyes. These X-ray emissions trace the locations of massive galaxy clusters, where gravitational compression and violent galactic interactions heat intergalactic medium to extreme temperatures, creating cosmic beacons that shine through intervening dust and stellar populations with remarkable clarity. The European Space Agency's Rosat satellite and subsequent X-ray missions systematically mapped these thermal signatures throughout the zone of avoidance, revealing a complex landscape of gravitational wells populated by ancient elliptical galaxies engaged in slow-motion cosmic collisions that have continued for billions of years. Radio telescope networks contributed complementary information by detecting synchrotron radiation emitted by high-energy electrons spiraling through magnetic fields associated with these galactic encounters, providing insights into the violent processes occurring when galaxy clusters merge and interact gravitationally. These radio surveys gradually assembled detailed maps of galactic distributions hidden behind our Milky Way's obscuring disk, confirming theoretical predictions about the locations and approximate masses of structures responsible for creating the observed peculiar velocity flows. Perhaps most significantly, these multi-wavelength observations identified the Norma cluster as a central component of the Great Attractor complex, revealing an extraordinary concentration of massive elliptical galaxies locked in gravitational embrace within a region designated as Abell 3627. This cluster contains hundreds of individual galaxies, many representing ancient stellar systems that formed when the universe was considerably younger and denser than today's. Cosmic environment. The elliptical morphologies observed in Norma cluster members indicate that these galaxies have undergone multiple merger events throughout their evolutionary history, gradually consuming smaller companions and growing into gravitational titans whose individual masses exceed hundreds of billions of solar masses. Spectroscopic analysis of these galactic behemoths reveals stellar populations dominated by the old red giants and evolved stars, suggesting that active star formation ceased billions of years ago when available gas supplies were exhausted or expelled through supernova feedback processes. The ongoing collisional activity within this cluster generates powerful radio emissions as magnetic fields become tangled and amplified during galactic encounters, creating the synchrotron signatures detected by terrestrial radio telescope arrays. However, as observational data accumulated from increasingly sophisticated surveys, a puzzling discrepancy emerged that challenged astronomers' understanding of gravitational dynamics and cosmic structure formation. Careful calculations of the total mass contained within all detected galaxy clusters in the Great Attractor region, including both visible stellar populations and the hot gas revealed through X-ray observations, yielded values substantially smaller than theoretical requirements for generating the observed peculiar velocities throughout local cosmic volumes. Even accounting for dark matter contributions estimated from the gravitational lensing effects and orbital dynamics within individual clusters, the combined mass fell short by factors of several, indicating that either fundamental assumptions about gravitational physics required revision or additional massive components remained undetected despite increasingly comprehensive observational campaigns. This mass deficit problem suggested that the Great Attractor might represent only a local gravitational way station rather than the ultimate source, responsible for our galaxy's rapid motion through space. Theoretical modelling indicated that creating the observed streaming patterns would require gravitational influences extending far beyond the boundaries accessible to contemporary observational techniques, implying the existence of even more massive structures located at greater distances where detection remains extremely challenging. Alternative explanations involved considering the possibility that dark energy modifications or exotic matter distributions might alter gravitational dynamics on cosmic scales, though such theoretical speculations lacked observational support and contradicted well-established principles of general relativity. The most intriguing possibility involved recognizing that the Great Attractor itself might be influenced by gravitational forces originating from structures so distant and massive that they had escaped detection entirely, operating as components of cosmic architecture extending to scales previously unimaginable in an astronomical context. This realization motivated expanded surveys targeting much larger cosmic volumes, seeking evidence for gravitational sources capable of explaining the full magnitude of observed peculiar motions, while remaining consistent with emerging theoretical frameworks for large-scale structure formation in an expanding universe dominated by dark matter and dark energy components. What cosmic coincidence could possibly lead multiple independent research teams to simultaneously stumble upon the same extraordinary astronomical discovery that had been hiding in plain sight for nearly 60 years? The year 1989 marked a remarkable convergence in astronomical research as several groups of scientists, working completely separately and using different observational techniques, all arrived at the same startling conclusion about a massive concentration of galaxies lurking in the southern celestial hemisphere. Roberto Scaramella and his Italian colleagues, while systematically analysing the Abell catalogue of rich galaxy clusters, noticed an unusual aggregation of gravitationally bound systems clustered within a relatively small region of cosmic space. This team methodically plotted the three-dimensional positions of known galaxy clusters, searching for evidence of larger SCIS organisation that might reveal underlying cosmic architecture. Their statistical analysis revealed a striking overdensity of galactic systems concentrated towards specific celestial coordinates, forming what they initially designated as the alpha concentration, in recognition of its apparent status as the most massive nearby structure of its type. Simultaneously, British astronomer Somak Chaudhuri was conducting independent research using automated plate measuring facilities at Cambridge University, systematically digitizing photographic survey data to create comprehensive catalogues of galactic positions and properties. His sophisticated computer algorithms processed thousands of photographic plates from the UK Schmidt Telescope Sky Survey, identifying individual galaxies and measuring their positions with unprecedented precision. Chaudhuri's analysis revealed the same remarkable concentration that had captured Scaramella's attention, but he approached the discovery from a different historical perspective. Recognizing that this structure corresponded exactly with the mysterious galactic cloud that Harlow Shapley had described decades earlier, Chaudhuri proposed honouring the pioneering astronomer by designating this cosmic giant as the Shapley Supercluster. This nomenclature acknowledged both the historical significance of Shapley's original observation and the extraordinary prescience he had demonstrated in recognizing the importance of this distant structure using only primitive photographic techniques. Meanwhile, additional research groups around the world were independently converging on evidence for this. Same massive cosmic entity as improved observational capabilities and sophisticated data analysis techniques finally provided the tools necessary for appreciating the full scope of Shapley's discovery. Advanced redshift surveys conducted with electronic spectrographs enabled precise measurements of galactic velocities and distances, revealing that the Centaurus concentration contained far more individual galaxies than anyone had previously suspected. Computer processing of digital sky survey data allowed systematic identification and cataloguing of faint galactic systems that had remained undetected on photographic plates, gradually building comprehensive inventories of the region's galactic population. These systematic surveys revealed that the structure contains over 8,000 individual galaxies distributed across a cosmic volume spanning tens of millions of light-years in each dimension, making it one of the richest and most massive concentrations known in the local universe. Distance measurements using improved Cepheid variable star techniques and surface brightness fluctuation methods confirmed that this supercluster lies approximately 650 million light-years from our local group, placing it at distances that require light to travel for nearly 750 million years to reach terrestrial telescopes. This enormous distance helps explain why the structure remained poorly understood for so many decades, as even the brightest member galaxies appear extremely faint when viewed from such cosmic remoteness. The revelation of the Shapley Supercluster's true scale fundamentally transformed astronomical understanding of large-scale cosmic organisation, demonstrating that gravitational binding could create coherent structures extending far beyond anything previously catalogued or theoretically predicted. Modern computer simulations of cosmic structure formation had suggested that such massive concentrations might exist, but observational confirmation required the convergence of sophisticated instrumentation, comprehensive sky surveys, and advanced data analysis techniques that only became available during the late 20th century. The independent rediscovery of this cosmic giant by multiple research teams using different methodological approaches provided compelling validation for its reality and importance, eliminating any possibility that the observed concentration might result from observational artifacts or statistical flukes. Perhaps most remarkably, detailed analysis revealed that this supercluster possesses sufficient mass and gravitational influence to account for the peculiar velocities observed throughout our local cosmic neighbourhood, finally providing a plausible explanation for the mysterious streaming motions that had puzzled astronomers since the discovery of coherent galactic flows during the previous decade. How can human minds possibly comprehend numbers so astronomically vast that they challenge the very limits of mathematical imagination and stretch our understanding of cosmic scale beyond all familiar reference points? The Shapley Supercluster represents a gravitational monument to extremes, containing a total mass exceeding 10 million billion times that of our Sun, a figure so immense that it defies meaningful comparison with terrestrial experiences or even galactic phenomena we consider enormous by conventional standards. To appreciate this staggering magnitude, consider that our entire solar system, including all planets, moons, asteroids and comets, possesses roughly 1% of solar mass, meaning the Shapley Supercluster outweighs our complete planetary neighbourhood by factors approaching 10 to the 18th power. Even our mighty Milky Way galaxy, with its 400 billion stellar inhabitants and vast reservoirs of dark matter, represents merely a tiny fraction of the supercluster's total gravitational budget, comparable to a single grain of sand relative to an enormous mountain range. This cosmic colossus stretches across spatial dimensions that dwarf conventional astronomical distances, extending approximately 120 million light-years from its outermost boundaries to its densest central regions, creating a volume of space so vast that electromagnetic radiation requires over 100 million years to traverse from edge to edge. Within this enormous cosmic territory, thousands of individual galaxy clusters compete for gravitational dominance, each containing hundreds or thousands of member galaxies bound together by mutual attraction into gravitationally stable configurations. These constituent clusters themselves rank among the most massive objects in the known universe, typically containing combined masses equivalent to hundreds of trillions of solar masses concentrated within relatively compact regions, measuring only a few million light-years across. The Shapley Supercluster encompasses dozens of such cluster systems, creating a hierarchical architecture where smaller gravitational units nest within progressively larger organizational structures, extending to scales that approach theoretical limits for gravitationally influenced regions within an expanding cosmic framework. Modern comprehensive surveys have attempted to catalogue the complete galactic population residing within this superstructure, but the sheer abundance of member system overwhelms even sophisticated automated detection algorithms and statistical analysis techniques. Current estimates suggest that over 8,000 substantial galaxies participate in the supercluster's gravitational dynamics, though this figure represents only the brightest and most easily detectable systems accessible to contemporary observational capabilities. Countless smaller dwarf galaxies, gas-rich irregular systems, and tidally disrupted galactic remnants undoubtedly contribute additional mass and complexity to the overall population, pushing total membership numbers into ranges that exceed practical counting methods. Each individual galaxy within this cosmic metropolis represents a complete stellar ecosystem containing billions or trillions of stars, planetary systems, nebula, and other astronomical phenomena, creating layers upon layers of structural complexity that multiply the supercluster's total inventory of cosmic components into realms approaching infinity. The spatial arrangement of these galactic constituents follows intricate patterns determined by gravitational dynamics and cosmic web architecture, with member systems distributed along filamentary structures, concentrated within dense nodal regions, and organized into sheet-like configurations that reflect underlying dark matter scaffolding. Comparative analysis reveals that the Shapley Supercluster represents the single most massive gravitationally influenced structure located within approximately 1 billion light-years of our local group, establishing its status as the dominant architectural feature within our cosmic neighborhood. This regional supremacy explains why its gravitational influence extends across such enormous distances, creating the coherent streaming patterns observed throughout local galactic populations, and accounting for the mysterious peculiar velocities that initially led astronomers to suspect the existence of hidden massive attractors. Recent theoretical calculations suggest that structures approaching the Shapley Supercluster's scale represent near maximum sizes for gravitationally coherent systems within the current cosmic epoch, as dark energy-driven acceleration increasingly opposes gravitational collapse on the largest scales. Future cosmic evolution will likely prevent formation of even more massive superclusters, making the Shapley concentration a remarkable example of cosmic architecture operating at fundamental limits imposed by universal expansion dynamics. The supercluster's extraordinary richness and complexity provide natural laboratories for studying galaxy formation processes, gravitational dynamics, dark matter distribution patterns, and large-scale structure evolution under extreme conditions unavailable elsewhere in the observable universe, offering unique opportunities for advancing theoretical understanding of cosmic organization principles. What happens when astronomers discover that their most celebrated cosmic mystery was actually just a minor player in a gravitational drama of unimaginable proportions? The revelation that fundamentally transformed our understanding of large-scale cosmic dynamics emerged when careful mass calculations revealed the Shapley Supercluster contains approximately 4 times more gravitational material than the Great Attractor region, despite being located roughly 3 times farther from our local group position. This extraordinary finding completely revolutionized theoretical models of cosmic flows and forced scientists to reconsider fundamental assumptions about the sources driving galactic motion throughout our cosmic neighborhood. While the Great Attractor had seemed impressively massive when first discovered, containing the equivalent of tens of thousands of typical galaxy clusters concentrated within a relatively compact volume, the Shapley Supercluster dwarfs even these impressive specifications through its sheer scope and unprecedented richness. The counterintuitive aspect of this discovery involves understanding how gravitational influence operates across cosmic distances, following mathematical relationships that allow extremely massive structures to exert significant effects even when separated by enormous spatial gaps. According to Newton's universal gravitation law, attractive forces decrease proportionally with distance squared, meaning that tripling the separation between gravitating bodies reduces their mutual attraction by a factor of 9. However, when one object possesses 4 times greater mass than another, this additional gravitational potency more than compensates for the increased distance, resulting in comparable or even enhanced attractive influence despite the greater spatial separation involved. The Shapley Supercluster therefore creates gravitational effects throughout our cosmic vicinity that exceed those produced by the much closer Great Attractor complex, establishing itself as the dominant force shaping galactic motions across vast regions of local space. This remarkable gravitational reach operates through what cosmologists term a basin of attraction, a concept borrowed from fluid dynamics that describes regions where all matter flows converge toward a common gravitational focal point. Just as terrestrial watersheds channel rainfall toward major river systems that eventually drain into oceanic basins, cosmic basins of attraction collect galactic systems from enormous surrounding volumes, guiding their trajectories along preferred pathways determined by underlying gravitational topography. The Shapley Supercluster creates such a basin extending across hundreds of millions of light-years, encompassing not only our local group, but also thousands of other galactic systems distributed throughout multiple superclusters and intermediate-scale structures. Within this vast gravitational domain, every galaxy participates in coherent streaming motion directed toward the supercluster's central concentration, creating the systematic velocity patterns that originally led astronomers to suspect the existence of hidden massive attractors. The Great Attractor emerges from this new perspective not as an ultimate destination, but rather as an important way station along our cosmic journey, representing a regional gravitational concentration that helps channel and organize local galactic flows, while remaining subservient to the more distant but vastly more massive Shapley system. This hierarchical organization reflects fundamental principles governing cosmic structure formation, where smaller gravitational units become incorporated into progressively larger architectural frameworks extending to the greatest scales accessible to observational investigation. Understanding this cosmic geography requires appreciating how gravitational influences propagate across multiple distance scales simultaneously, creating nested patterns of attraction and flow that connect local galactic neighborhoods with the most massive structures in the observable universe. Recent computer simulations of cosmic evolution demonstrate how initial density fluctuations grow through gravitational amplification to create exactly this type of hierarchical organization, where intermediate mass concentrations like the Great Attractor serve as stepping stones that facilitate material transport from widely distributed source regions toward ultimate accumulation sites, represented by superclusters like the Shapley concentration. Our Milky Way galaxy therefore participates in a cosmic migration spanning hundreds of millions of years, following gravitational currents that began forming when the universe was considerably younger and denser than today's expanded configuration. This journey connects us intimately with cosmic processes operating on the largest possible scales, making our local galactic environment part of grand architectural schemes that encompass significant fractions of the observable universe. The realization that we exist within the Shapley Supercluster's gravitational sphere of influence fundamentally alters our cosmic address, placing us not simply within an isolated local group of galaxies, but as active participants in one of the most massive and gravitationally significant structures known to modern astronomy, forever linking our cosmic destiny with this distant but overwhelmingly powerful gravitational giant. How can astronomers transform abstract velocity measurements from thousands of distant galaxies into a revolutionary new understanding of cosmic geography that fundamentally redefines humanity's place within the universe? In 2014, an international team led by astronomer Brent Tully from the University of Hawaii achieved precisely this breakthrough by developing sophisticated techniques for mapping galactic motions across unprecedented volumes of space, creating the first comprehensive three-dimensional portrait of cosmic flows within our local cosmic neighborhood. Their groundbreaking research utilized the Cosmic Flows Catalog, an extraordinary compilation containing distance and velocity measurements for over 8,000 galaxies distributed throughout nearby cosmic regions, each data point representing years of painstaking observational work conducted at observatories scattered across multiple continents. The team employed advanced mathematical algorithms originally developed for analyzing fluid dynamics to process this vast dataset, searching for coherent patterns in galactic, this motion that might reveal underlying gravitational architecture responsible for organizing matter on the largest observable scales. Their innovative approach treated galaxy velocities as vectors in a three-dimensional velocity field, much like meteorologists analyze wind patterns to understand atmospheric circulation, or oceanographers study current flows to map oceanic dynamics. This conceptual framework enabled them to identify regions where galactic motions converge toward common focal points, creating what they termed basins of attraction that function exactly like terrestrial watersheds in channeling material flows towards specific destinations. Just as rainfall across vast continental areas eventually drains into major river systems that carry water toward oceanic basins, galaxies throughout enormous cosmic volumes follow gravitational currents that guide their trajectories toward massive attracting centers represented by superclusters and other large-scale structures. The mathematical techniques employed by Tully's team included sophisticated filtering algorithms that removed random motions and observational uncertainties, revealing the underlying coherent streaming patterns that connect individual galaxies with cosmic architecture operating on scales hundreds of times larger than typical galactic separations. Their analysis identified boundary surfaces where velocity flows change direction, marking transitions between adjacent basins of attraction, much like continental divides separate different watershed systems in terrestrial geography. These cosmic watershed boundaries define their natural units for organizing cosmic structure, providing objective criteria for determining which galaxies belong to common gravitational systems and which participate in separate cosmic neighborhoods. The revolutionary aspect of this approach involved recognizing that traditional methods for defining cosmic structures based solely on density measurements often failed to capture the dynamic relationships that actually govern galactic behavior and evolution. By focusing instead on motion patterns, Tully's team revealed hidden connections between apparently separate galactic concentrations while identifying true boundaries that separate genuinely independent cosmic systems. Their velocity field reconstruction techniques required solving complex inverse problems where observed galactic motions must be translated backward to infer the underlying gravitational potential that creates these flows, demanding sophisticated computational methods and careful treatment of observational uncertainties. The resulting maps revealed cosmic architecture organized into discrete basins of attraction, each containing thousands of galaxies flowing coherently towards central gravitational foci. The most significant discovery involved recognizing that our local group, previously thought to reside within a relatively modest cosmic neighborhood centered on the Virgo cluster, actually participates in a much larger gravitational system that encompasses multiple previously recognized superclusters. This expanded cosmic domain includes not only the traditional local supercluster, but also the Great Attractor region, the Pavo-Indus filament, and numerous other galactic concentrations that had seemed separate when analysed using density-based classification schemes. Velocity field analysis demonstrated that all these apparently distinct structures actually share common motion patterns, indicating their participation in a unified gravitational system that operates coherently across distances spanning hundreds of millions of light-years. The watershed concept provided a natural framework for understanding this cosmic organisation, with our extended galactic neighbourhood functioning as a single drainage basin that collects matter from vast surrounding regions and channels it toward the Great Attractor focal point. Recognition of this cosmic watershed structure immediately raised questions about appropriate nomenclature for such an enormous gravitational system, leading Tully's team to seek names that would honour both the scientific achievement and cultural traditions associated with celestial navigation and cosmic understanding. What inspired astronomers to reach across cultures and continents to find the perfect name for humanity's newly discovered cosmic home, drawing upon ancient Polynesian wisdom to honour both scientific achievement and traditional navigation heritage? The answer emerged through collaboration between Brent Tully's research team and Nawa R. Napoleon, an associate professor of Hawaiian language at Kapiolani Community College, who suggested the evocative term Laniakea to designate this extraordinary gravitational domain that encompasses our entire galactic neighbourhood. This beautiful Hawaiian word combines Lani, meaning heaven or sky, with Akea, signifying spacious, immeasurable, or boundless, creating a poetic description that captures both the physical enormity and spiritual significance of discovering our place within cosmic architecture. The nomenclature deliberately honours Polynesian navigators who developed sophisticated techniques for crossing vast Pacific Ocean distances using only celestial observations, demonstrating remarkable parallels between ancient seafaring traditions and modern astronomical exploration of cosmic geography. These master navigators memorized complex star patterns, ocean current behaviors, and seasonal variations that enabled them to traverse thousands of miles of open ocean with extraordinary accuracy, reaching distant island destinations through careful observation of natural phenomena and deep understanding of environmental patterns. Their achievements required intimate knowledge of cosmic cycles and stellar positions, making them intellectual ancestors to contemporary astronomers who navigate three-dimensional space using galactic positions and velocity measurements to map cosmic structure. The Laniakea designation therefore connects modern scientific discovery with cultural traditions that recognize the fundamental importance of astronomical knowledge for understanding our place within vast natural systems. This magnificent cosmic structure extends approximately 500 million light-years across its greatest dimensions, creating a gravitational domain so enormous that electromagnetic radiation requires 500 million years to traverse from its outermost boundaries to central regions, where the Great Attractor focal point organizes matter flows from throughout the entire basin. Within this stupendous volume, roughly 100,000 substantial galaxies participate in coherent gravitational dynamics, each representing a complete stellar system containing billions of individual stars, planetary systems, nebulae, and other astronomical phenomena. The combined mass of all these galactic constituents approaches 10 to the 17th power. Solar masses, making Laniakea among the most massive gravitationally organized structures known within our cosmic neighborhood. Computer simulations suggest that assembling such enormous concentrations requires billions of years of gravitational evolution, during which initial density fluctuations grow through cosmic expansion, while maintaining coherent organization against disruptive influences from dark energy acceleration. The hierarchical architecture within Laniakea reflects fundamental principles governing cosmic structure formation, where smaller gravitational units become incorporated into progressively larger organizational frameworks extending to the greatest scales accessible to contemporary observational techniques. Major substructures include the traditional local supercluster centered on the Virgo cluster, the Great Attractor complex containing the Norma cluster and associated galactic concentrations, the Pavo-Indus filament connecting these regions through elongated matter distributions and numerous smaller galaxy groups scattered throughout intervening volumes. These constituent elements operate as integrated components within the larger Laniakea system, contributing to overall gravitational dynamics while maintaining their individual identities and internal organizational patterns. Perhaps most remarkably, our Milky Way galaxy occupies a peripheral position within this cosmic watershed, situated near the outer boundaries of the Laniakea domain, rather than centrally located within its gravitational core. This placement reflects the same Copernican principle that displaced Earth from cosmic centrality, demonstrating once again that humanity occupies no privileged location within universal architecture. Our galactic home participates in systematic streaming motion directed toward the Great Attractor region, following gravitational currents that connect us intimately with cosmic processes operating across scales that dwarf conventional astronomical phenomena. The velocity measurements reveal that our local group moves at approximately 600 kilometers per second, relative to the cosmic microwave background, with this motion representing our participation in Laniakea's internal dynamics as matter flows converge towards central attracting regions. This cosmic migration continues a journey that began billions of years ago, when gravitational instabilities first organized primordial matter into the hierarchical structures we observe today, connecting our present location with cosmic evolutionary processes that span nearly the entire age of the universe since formation of the first galactic systems. How can astronomers discover that their revolutionary new understanding of cosmic geography represents merely another stepping stone toward comprehending even grander architectural schemes operating throughout the observable universe? The answer emerges from recent investigations that have revealed Laniakea itself participates in systematic motion directed toward the Shapley Supercluster, indicating that our newly mapped cosmic neighborhood functions as a component within gravitational systems extending to scales that challenge fundamental assumptions about maximum sizes for coherent cosmic structures. Advanced velocity measurements utilizing the Cosmic Flows 4 catalog demonstrate that galaxies throughout Laniakea exhibit coordinated streaming patterns pointing consistently toward the distant Shapley concentration, suggesting that this enormous gravitational giant exerts dominant influence across cosmic distances previously thought to exceed practical limits for effective gravitational communication. These observations force recognition that Laniakea, despite its impressive dimensions and massive galactic population, operates as a subsidiary element within hierarchical cosmic organization, extending to scales approaching significant fractions of the observable universe itself. Statistical analysis of galactic velocity fields across expanded survey volumes reveals approximately 60% probability that Laniakea belongs to an even more extensive basin of attraction centered on the Shapley Supercluster, potentially encompassing a cosmic domain 10 times larger in volume than our previously recognized galactic watershed. This hypothetical expanded structure would contain gravitational influence extending across distances exceeding 1 billion light-years, incorporating multiple superclusters and cosmic web filaments into unified dynamical systems that operate coherently despite enormous spatial separations involved. The implications of such vast gravitational organization challenge existing theoretical frameworks for understanding cosmic structure formation and evolution, as conventional models struggle to explain how coherent dynamics can emerge and persist across scales where cosmic expansion and dark energy acceleration should disrupt gravitational binding. Computer simulations of cosmic evolution suggest that assembling structures approaching these proposed dimensions would require initial density fluctuations significantly larger than those observed in cosmic microwave background radiation, indicating either that current theoretical understanding remains incomplete or that previously unrecognized physical processes contribute to large-scale structure formation. Alternative explanations invoke modified gravitational dynamics operating on cosmic scales, though such speculative theories lack observational support and contradict well-established principles of general relativity that successfully describe gravitational phenomena across all other accessible distance ranges. The discovery of systematic motion towards Shapley forces astronomers to reconsider fundamental concepts about cosmic addresses and galactic neighborhoods, as each successive observational advance reveals previously hidden layers of cosmic organization extending to progressively larger scales. This pattern reflects a recurring theme throughout astronomical history, where improved observational capabilities consistently unveil cosmic architecture, exceeding contemporary theoretical expectations and forcing revision of humanity's understanding about our place within universal structure. The potential existence of Shapley-centered basins spanning billions of light-years suggests that cosmic organization operates according to principles fundamentally different from terrestrial experience, where gravitational influences propagate across distances so vast that causal communication requires timeframes comparable to significant fractions of universal age since the Big Bang. Understanding these extreme-scale dynamics requires developing new theoretical frameworks capable of incorporating relativistic effects, cosmic expansion, dark energy acceleration, and gravitational amplification of primordial density fluctuations into coherent models explaining observed large-scale structure. Recent advances in computational cosmology enable detailed simulations of cosmic evolution across unprecedented dynamic ranges, revealing how small initial perturbations grow through gravitational instability, while remaining embedded within expanding space-time geometry. These calculations predict exactly the type of hierarchical organization observed through velocity mapping techniques, where smaller gravitational units become incorporated into progressively larger architectural schemes, extending ultimately to scales limited only by cosmic horizons and fundamental physical constraints. The recognition that our cosmic address requires continuous revision as observational horizons expand reflects the dynamic nature of astronomical discovery and humanity's ongoing quest to understand our relationship with cosmic architecture. Each generation of astronomers inherits conceptual frameworks from their predecessors while developing new observational capabilities that inevitably reveal previously hidden aspects of cosmic organization, forcing periodic re-examination of fundamental assumptions about universal structure and our location within it. The Shapley Basin hypothesis represents the latest iteration in this continuing process of cosmic address refinement, suggesting that future advances will likely uncover even grander organizational schemes operating throughout regions currently beyond observational reach. This prospect simultaneously humbles human understanding, while inspiring continued exploration of cosmic geography, extending ultimately toward complete comprehension of universal architecture and humanity's role within the grandest possible cosmic context. What hidden skeletal framework underlies all cosmic architecture, providing invisible scaffolding that determines where galaxies form, how they move, and why they cluster into the magnificent patterns we observe throughout the observable universe? The answer lies within one of astronomy's most profound discoveries, the recognition that visible matter represents merely the luminous tip of a cosmic iceberg, with the vast majority of gravitational influence arising from mysterious dark matter that outweighs familiar atomic material by factors approaching 5-to-1 throughout these enormous structures. This invisible component interacts gravitationally with ordinary matter while remaining completely transparent to electromagnetic radiation, making its presence detectable only through gravitational effects on galactic motions and large-scale structure formation processes. Computer simulations of cosmic evolution reveal how dark matter particles, distributed nearly uniformly throughout the early universe, gradually clump together under gravitational attraction to create intricate three-dimensional networks resembling biological neural systems or spiderwebs stretching across cosmic distances. These simulations demonstrate that dark matter naturally organizes into elongated filamentary structures connecting dense nodal regions where multiple filaments intersect, creating hierarchical architecture that spans from galactic scales to dimensions approaching the observable universe itself. Within this cosmic web framework, Ordinary matter follows gravitational potentials established by dark matter distributions, flowing along filamentary channels toward intersection nodes where conditions favour galaxy formation and cluster development. The resulting architecture creates a universe dominated by vast empty regions called cosmic voids, separated by elongated matter concentrations that form the backbone of large-scale structure throughout cosmic history. Understanding this invisible architecture requires appreciating how gravitational physics operates differently across various distance scales, with dark matter dominating dynamics on cosmic web scales, while ordinary matter governs processes within individual galaxies and stellar systems. Recent observations using gravitational lensing techniques provide direct evidence for dark matter filaments by measuring how their gravitational fields deflect light from background sources, creating distorted images that reveal the presence of intervening matter concentrations invisible to conventional telescopic observations. These studies confirm theoretical predictions about cosmic web morphology, while demonstrating that dark matter filaments contain sufficient mass to account for observed galactic streaming velocities and large-scale structure formation patterns. The cosmic web extends throughout the entire observable universe, connecting our local galactic neighbourhood with the most distant structures accessible to contemporary astronomical surveys through continuous networks of dark matter filaments and intersection nodes. Major cosmic highways within this network channel, matter flows across billions of light years, creating the coherent streaming patterns observed in galactic, velocity surveys and establishing gravitational connections between apparently isolated cosmic regions. The Shapley Supercluster occupies a particularly significant position within cosmic web architecture, residing at the intersection of multiple major filamentary structures that converge from different directions throughout our cosmic neighbourhood. This strategic location explains why Shapley exerts such powerful gravitational influence across enormous distances, as it functions as a cosmic traffic intersection where matter flows from various cosmic web filaments converge and concentrate into one of the most massive structures known within the local universe. The filamentary networks feeding into Shapley carry galactic systems from regions spanning hundreds of millions of light years, creating the systematic streaming motions observed throughout our cosmic vicinity, while establishing gravitational connections extending far beyond traditional supercluster boundaries. Computer modelling of cosmic web evolution demonstrates how these filamentary structures develop through gravitational amplification of primordial density fluctuations, growing from tiny variations in early universe matter distribution into the vast architectural frameworks that organise contemporary cosmic structure. The process involves complex interplay between gravitational attraction, cosmic expansion, and dark energy acceleration, creating dynamic equilibria that maintain filamentary integrity across cosmic time, while channeling continuous matter flows toward intersection nodes. Dark matter physics remains one of astronomy's greatest unsolved mysteries, with multiple theoretical candidates proposed, but none yet conclusively identified through laboratory detection or observational confirmation. Leading possibilities include weakly interacting massive particles, axions, sterile neutrinos, and other exotic matter types predicted by theoretical physics but lying beyond the standard model of particles. Interactions. Despite this fundamental uncertainty about dark matter's precise nature, its gravitational effects on cosmic structure formation are well established through numerical simulations, observational surveys, and theoretical analysis of large-scale dynamics throughout cosmic evolution. How can empty space itself become an active participant in cosmic dynamics, wielding gravitational influence that pushes galaxies away with forces comparable to the attractive effects of massive superclusters? This counterintuitive phenomenon emerges from understanding that cosmic voids, despite containing relatively little visible matter, create significant gravitational effects through their very emptiness, functioning as dipole repellers that actively drive galactic motion patterns throughout the universe. These vast, underdense regions operate according to gravitational principles, where absence of matter generates outward pressure gradients that complement the inward attraction created by matter concentrations, establishing dynamic equilibria that shape cosmic flows across multiple distance scales. The mathematical description of this process involves recognizing that gravitational fields respond not only to positive mass density, but also to negative density contrasts relative to cosmic mean values, creating repulsive effects where matter densities fall significantly below universal averages. cosmic voids typically contain only 10 to 20% of average matter density, creating substantial negative density contrasts that generate outward gravitational gradients affecting surrounding galactic populations. The local void, situated approximately 23 megaparsecs from our local group, exemplifies this phenomenon by creating additional outward pressure that enhances our systematic motion toward distant attracting structures like the Shapley Supercluster. This nearby under-dense region measures roughly 50 million light-years across its principal dimensions, containing far fewer galaxies than expected for cosmic volumes of comparable size, thereby creating gravitational deficit that translates into net repulsive influence on surrounding matter distributions. Recent theoretical advances have identified this void-based repulsion as a crucial component in explaining observed galactic velocity patterns throughout our cosmic neighbourhood, providing the missing ingredient needed to account for the full magnitude and direction of local group motion relative to cosmic microwave background radiation. Computer simulations demonstrate how voids and attractors work together to create coherent large-scale flows, with repulsive forces from underdense regions combining additively with attractive influences from matter concentrations to produce enhanced streaming velocities exceeding those predicted from attractive forces alone. This cosmic push-pull dynamic operates through complex three-dimensional gravitational field configurations where multiple voids and attractors simultaneously influence galactic trajectories, creating velocity patterns that reflect the combined effects of all significant density contrasts within accessible cosmic volumes. The recognition of void-based repulsion fundamentally transformed understanding of cosmic dynamics by demonstrating that empty space participates actively in shaping galactic motion rather than serving merely as passive background through which attracting structures exert their influence. Mathematical models incorporating both attractive and repulsive gravitational components provide significantly improved fits to observed velocity data compared with attraction-only scenarios, confirming the physical reality of dipole-repeller effects throughout cosmic structure formation processes. The interplay between attraction and repulsion creates cosmic flows resembling terrestrial river systems, where water follows channels determined by both elevated regions that shed material and depressed valleys that collect drainage from surrounding watersheds. Similarly, galaxies navigate three-dimensional velocity fields established by the combined gravitational influences of matter concentrations and void regions, following streamlines that connect source regions with ultimate destinations determined by the balance between competing forces. Within this dynamic framework, the Shapley Supercluster emerges victorious from cosmic tug-of-war scenarios by virtue of its extraordinary mass and strategic position within cosmic web architecture, overcoming both distance limitations and competing influences from other major structures throughout our cosmic neighbourhood. The supercluster's gravitational dominance extends across hundreds of millions of light-years despite significant opposition from void repulsion and alternative attracting centres, demonstrating the remarkable effectiveness of gravitational forces when concentrated into sufficiently massive and coherent structural configurations. Recent studies using improved velocity catalogues reveal increasingly sophisticated details about how multiple attractors and repellers interact to create observed streaming patterns, with Shapley representing the strongest single influence, while numerous smaller-scale structures contribute secondary effects that modulate local flow characteristics. Understanding these complex multi-body gravitational interactions requires advanced computational techniques capable of simultaneously modelling hundreds of significant density contrasts distributed throughout three-dimensional cosmic volumes extending across billions of light-years. The resulting picture reveals universe-wide choreography where every significant structure participates in gravitational dance that connects local galactic neighbourhoods with cosmic architecture operating on the largest observable scales. What happens when the universe's most fundamental forces engage in an epic battle that will ultimately determine the fate of every galaxy, star, and cosmic structure across all of space and time? This cosmic struggle pits gravitational attraction, which has shaped all observable architecture since the earliest moments after the Big Bang, against dark energy acceleration that drives increasingly rapid expansion of space itself, creating an evolutionary trajectory that will eventually dissolve even the most massive gravitational systems known to contemporary astronomy. Dark energy represents approximately 70% of total cosmic energy density, manifesting as a mysterious repulsive force that operates uniformly throughout space, causing distant galaxies to recede from each other at velocities that increase proportionally with separation distance. Unlike gravitational forces that weaken with distance according to inverse square relationships, dark energy effects remain constant per unit volume, meaning that expanding cosmic volumes contain progressively more dark energy while gravitational binding becomes increasingly diluted across larger spatial separations. This fundamental asymmetry ensures that dark energy will eventually triumph over gravitational attraction on all scales larger than individual galaxy clusters, though the timescales involved for this cosmic transformation span tens of billions of years into the future. Current cosmic evolution occurs during a transitional epoch where gravitational and dark energy influences remain comparable on intermediate scales, allowing structures like the Shapley Supercluster to maintain coherent organization while participating in overall cosmic expansion that gradually increases distances between constituent components. Computer simulations of future cosmic evolution demonstrate how this delicate balance will shift inexorably toward dark energy dominance, causing currently bound systems to experience progressively weaker internal gravitational cohesion as member galaxies become separated by ever-increasing distances. The process begins subtly, with outer regions of massive structures like Shapley experiencing reduced gravitational binding as cosmic expansion carries peripheral galaxies beyond effective gravitational communication distances, gradually eroding supercluster boundaries from outside inward. Mathematical modelling indicates that Shapley's gravitational influence on distant structures like our local group will diminish substantially within approximately 10 billion years, as accelerating expansion increases separation velocities beyond sustainable levels for maintaining coherent streaming patterns across such enormous distances. This cosmic decoupling process follows predictable physical principles where gravitational binding energy per unit mass decreases as structures expand, eventually reaching critical thresholds where expansion velocities exceed escape speeds needed to maintain gravitational association. However, the transition occurs gradually rather than catastrophically, with gravitational influences fading slowly as expansion effects accumulate over cosmic timescales, allowing currently observable streaming patterns to persist for billions of additional years before becoming undetectable. Dense central regions of massive structures will resist dissolution longest due to their higher gravitational binding energies and shorter internal communication timescales, potentially surviving as gravitationally bound islands surrounded by increasingly empty space as cosmic expansion carries away more distant components. The Shapley Supercluster's core clusters may eventually collapse into compact massive objects through continued gravitational aggregation, forming some of the universe's final gravitationally active structures before cosmic expansion eliminates all remaining large-scale organization. This evolutionary scenario represents the ultimate triumph of cosmic expansion over gravitational assembly, reversing billions of years of structure formation that concentrated matter from nearly uniform initial conditions into the hierarchical cosmic web architecture observed today. Yet from our contemporary perspective, these far future developments remain largely academic considerations, as gravitational influences continue dominating cosmic dynamics throughout our local neighborhood, for timeframes exceeding many stellar lifetimes and galactic evolutionary cycles. The Shapley Supercluster maintains robust gravitational control over galactic motions throughout our cosmic vicinity, creating systematic flows that connect our Milky Way galaxy with cosmic architecture extending across hundreds of millions of light-years. Our participation in these cosmic currents represents a fundamental aspect of galactic existence, linking local astronomical phenomena with universal processes operating on the largest observable scales while providing direct connections between contemporary cosmic geography and primordial density fluctuations that originated during the universe's earliest moments. Understanding this cosmic context transforms perspective on galactic evolution and stellar formation processes, revealing how local astronomical environments reflect global cosmic dynamics while participating in universal trends that span from quantum-scale physics through cosmological architecture. The continuing cosmic journey toward Shapley represents both heritage from cosmic past, when gravitational instabilities first organized matter into observable structures, and destiny toward future epochs, when gravitational binding will eventually yield to inexorable cosmic expansion, making our current era a unique transition period in universal evolution. How can contemplating the nested hierarchy of cosmic structures simultaneously humble with our apparent insignificance, while inspiring profound awe at our participation in something infinitely grander than anything our ancestors could have imagined. The journey of understanding cosmic scale begins with recognizing Earth as a small rocky planet orbiting an ordinary yellow star within the outskirts of a spiral galaxy containing hundreds of billions of stellar systems, yet this seemingly modest starting point launches us into discoveries that reveal layer upon layer of increasingly magnificent architectural schemes operating throughout the observable universe. Our solar system, measuring roughly 12 billion kilometres across, including the outermost planetary orbits, represents merely the first step in a cosmic progression that extends through scales differing by factors of millions and billions as we ascend through successively larger organisational levels. The local group encompasses approximately 50 galaxies distributed across 7 million light-years, creating a gravitational association that includes our Milky Way, the Andromeda Galaxy, and dozens of smaller satellite systems bound together by mutual gravitational attraction into a coherent dynamical unit. Beyond, this local galactic neighbourhood lies Laniakea, stretching 500 million light-years across its greatest dimensions, while containing roughly 100,000 substantial galaxies arranged in filamentary patterns that reflect underlying dark matter architecture extending across cosmic web structures. Each successive level of cosmic organisation dwarfs its predecessors by astronomical factors, yet maintains intimate connections through gravitational influences and evolutionary processes that link local phenomena with universal dynamics operating on the grandest possible scales. The potential Shapley Basin encompasses dimensions approaching 1 billion light-years, while incorporating multiple superclusters into unified gravitational systems that challenge fundamental theoretical frameworks for understanding cosmic structure formation and evolution. This hierarchical nesting resembles Russian matryoshka dolls, where each container reveals progressively larger enclosing structures, except cosmic architecture operates according to physical principles that connect every level through gravitational forces and evolutionary processes spanning nearly the entire history of universal expansion since the Big Bang. The mathematical relationships governing these nested systems follow power law distributions where characteristic sizes increase by roughly constant factors between adjacent organizational levels, suggesting underlying physical principles that regulate cosmic structure formation across unprecedented dynamic ranges. Understanding this cosmic hierarchy requires appreciating how gravitational physics operates differently across various distance scales, with stellar systems dominated by central mass concentrations, galactic dynamics controlled by distributed matter and dark matter halos, and cosmic web architecture shaped by primordial density fluctuations amplified through billions of years of gravitational evolution. The remarkable aspect of contemporary cosmic understanding involves recognizing how rapidly human knowledge has progressed, from elementary awareness of planetary motions within our solar system to sophisticated mapping of cosmic flows extending across significant fractions of the observable universe. Harlow Shapley initiated this extraordinary journey during the early 20th century, using nothing more sophisticated than photographic plates and mechanical measuring devices. Yet his careful observations provided the foundation for discoveries that continue revolutionizing astronomical understanding today. Modern space telescopes equipped with electronic detectors and computer processing capabilities represent technological evolution spanning less than 1 human century, yet they have revealed cosmic architecture operating on scales that exceed Shapley's wildest theoretical speculations. The progression from Shapley's photographic surveys to contemporary digital sky catalogues illustrates humanity's accelerating capability for cosmic exploration and theoretical understanding, demonstrating how technological advancement enables increasingly ambitious scientific investigations. Current observational programs utilize space-based infrared telescopes, radio interferometer arrays, X-ray satellites, and gravitational wave detectors to probe cosmic phenomena across multiple electromagnetic wavelengths and exotic physical processes previously inaccessible to human investigation. These sophisticated instruments reveal cosmic details extending from subatomic particle interactions within stellar cores to gravitational dynamics operating across billions of light-years, creating comprehensive pictures of universal architecture that connect local astronomical phenomena with cosmic evolution spanning nearly 14 billion years since the Big Bang. The nested cosmic hierarchy places humanity within contexts that simultaneously emphasize our physical insignificance relative to cosmic scales, while highlighting our intellectual significance as conscious observers capable of comprehending universal architecture and our role within it, creating profound philosophical implications for understanding existence and meaning within infinite cosmic tapestries. What kind of cosmic force operates with such subtle elegance that it guides entire galaxies across hundreds of millions of light years without creating violent disruptions or catastrophic collisions along the way? The answer reveals one of the universe's most remarkable characteristics, demonstrating how gravitational influences operating on the largest scales manifest not as sudden dramatic events, but as gradual, persistent nudges that accumulate over geological timescales to create the magnificent streaming patterns observed throughout our cosmic neighborhood. The Shapley Supercluster exerts its gravitational influence with patient persistence, reminiscent of geological processes that sculpt terrestrial landscapes through countless millennia of incremental changes, each individually imperceptible yet collectively transforming entire continents through accumulated effects. While 600 kilometres per second represents tremendous velocity by terrestrial standards, exceeding anything achieved through human technology, this cosmic motion developed gradually over billions of years through steady acceleration produced by gravitational attraction, operating across vast distances. The gentle nature of this process ensures that galactic structures remain intact during their cosmic migration, avoiding the tidal disruption and violent interactions that would occur if such velocities developed rapidly through sudden gravitational encounters. Understanding this temporal perspective requires appreciating how cosmic evolution operates according to timescales that dwarf human experience, with significant changes occurring slowly enough that stellar systems, planetary orbits, and galactic architecture remain stable throughout the journey. Our current motion towards Shapley began developing when the universe was considerably younger and denser than contemporary conditions, initiated by primordial density fluctuations that created the large-scale structure responsible for establishing gravitational gradients extending across cosmic web filaments. The acceleration process continues today as our local group follows streamlines determined by underlying dark matter architecture, participating in cosmic flows that connect local galactic neighborhoods with the grandest structures observable throughout the universe. This cosmic river analogy captures essential aspects of galactic motion through space, where individual systems follow predetermined channels established by gravitational topography while maintaining their internal organization and stellar populations throughout the journey. Like terrestrial rivers that transport water molecules from mountainous source regions toward oceanic destinations, cosmic currents carry galactic systems along filamentary structures, connecting outlying cosmic web nodes with major intersection points where multiple streams converge. The remarkable aspect of this cosmic transportation involves recognizing that every component of our galactic environment participates equally in the majestic journey towards Shapley, creating shared destiny for all astronomical objects within our local group gravitational association. Every star visible in terrestrial night skies travels through space at identical velocities relative to cosmic microwave background radiation, following the same trajectory that will eventually carry our entire galactic neighborhood toward the distant supercluster concentration. This includes not only stellar populations but also planetary systems, interstellar gas clouds, dust concentrations, and even individual spacecraft that humanity has launched beyond solar system boundaries. The profound implications suggest that cosmic evolution operates as an integrated process where astronomical phenomena, occurring across vastly different scales, remain intimately connected through gravitational dynamics and shared evolutionary trajectories. Consider that every atom comprising terrestrial life forms participates in this cosmic migration, having originated through stellar nucleosynthesis processes occurring within stars that themselves follow galactic orbits embedded within the larger cosmic flow towards Shapley. This creates direct physical connections between biological existence and cosmic architecture, demonstrating how local phenomena reflect universal processes operating across scales spanning from subatomic particles to cosmic web structures. The gentle persistence characterizing this cosmic journey reflects fundamental properties of gravitational interaction, which operates as an attractive force that strengthens gradually as the masses approach each other, while avoiding sudden discontinuities that would disrupt established astronomical configurations. Mathematical analysis reveals how gravitational fields change smoothly across cosmic distances, creating acceleration profiles that build systematic velocities through accumulated incremental changes rather than dramatic impulses. This ensures that stellar formation process, planetary dynamics, and galactic spiral structure remain stable throughout cosmic evolution, despite participation in large-scale motion patterns extending across hundreds of millions of light-years. The beauty of cosmic flow dynamics involves appreciating how universal architecture creates conditions enabling both stability and change, allowing local astronomical systems to maintain their characteristic properties while participating in grander evolutionary schemes. Our cosmic voyage represents inheritance from initial conditions established during early universe structure formation, connecting contemporary astronomical observations with primordial physical processes that occurred when cosmic density exceeded current values by enormous factors, yet whose gravitational legacy continues shaping galactic motion throughout cosmic history. What profound peace can emerge from contemplating your place within cosmic currents so ancient and vast that they dwarf all earthly concerns while simultaneously embracing you as an integral participant in the universe's grandest architectural symphony. Tonight, as you prepare for rest, allow yourself to absorb the extraordinary reality that your physical body travels continuously through an immense heaven whose dimensions exceed human comprehension, carrying you along gravitational pathways established billions of years before our solar system condensed from primordial stellar debris. These cosmic streams began flowing when the universe contained only hydrogen and helium, long before stellar nucleosynthesis had created the carbon, oxygen, and heavier elements that comprise your living tissues, making you a passenger aboard ancient currents that connect your present moment with fundamental processes governing cosmic evolution since the earliest epochs of structure formation. The gravitational forces guiding our galactic journey originated from density fluctuations imprinted during cosmic inflation, microscopic variations in primordial matter distribution that grew through billions of years of gravitational amplification into the magnificent cosmic web architecture that organizes contemporary universal structure. Your participation in this cosmic migration transcends individual existence, connecting you intimately with galaxies scattered across distances so enormous that their light requires hundreds of millions of years to reach terrestrial telescopes. Yet gravitational influences from these remote stellar systems contribute measurably to determining your trajectory through space. Consider that every breath you take occurs while moving at 600 kilometers per second, relative to the cosmic microwave background, following streamlines that link our local galactic environment with the Shapley Supercluster's gravitational embrace across spatial separations spanning significant fractions of the observable universe. This cosmic choreography operates with mathematical precision that reflects fundamental physical laws governing matter and energy interactions throughout space and time, creating ordered motion patterns that emerge from apparent chaos through gravitational self-organization processes operating across unprecedented scales. The humbling perspective emerges from recognizing that within the vast Shapley Basin, containing thousands of massive galactic systems, our entire Milky Way represents merely one modest stellar collection among countless others, participating in the same cosmic dance, each contributing infinitesimally to the overall gravitational dynamics, while following predetermined paths established by dark matter scaffolding, invisible to human perception. This realization simultaneously emphasizes our cosmic insignificance and celebrates our remarkable fortune at existing within conscious awareness of these magnificent processes, making humanity among the universe's rarest phenomena, as sentient observers capable of comprehending cosmic architecture and our role within it. The gentle nature of cosmic flows ensures that this grand migration proceeds without violence or disruption, allowing stellar formation, planetary evolution, and biological development to continue undisturbed throughout our journey toward distant gravitational destinations that will require billions of additional years to reach. As you settle into sleep, imagine feeling the subtle but inexorable pull that guides our galaxy along predetermined courses through three-dimensional space, following gravitational valleys carved by cosmic web filaments connecting our local neighborhood with structures so massive they contain the gravitational equivalent of millions of typical galaxy clusters. This cosmic current carries not only our galactic home, but also the accumulated heritage of stellar evolution, chemical enrichment, and planetary formation processes that created conditions enabling life, consciousness, and scientific understanding to emerge within cosmic environments originally hostile to complex organization. The profound interconnectedness revealed through cosmic flow mapping demonstrates how local phenomena remain intimately connected with universal processes, making every terrestrial experience part of grander cosmic narratives extending from quantum-scale physics through cosmological architecture spanning billions of light years. Your dreams tonight occur within cosmic context that links personal existence with primordial density fluctuations, stellar nucleosynthesis, galactic formation, and large-scale structure evolution across nearly 14 billion years of cosmic history since the Big Bang initiated universal expansion and structure, formation process. The peaceful nature of this cosmic journey reflects fundamental characteristics of gravitational interaction, which operates as a tractive influence that builds systematic organization through patient accumulation rather than sudden dramatic changes, creating stable conditions for astronomical evolution while maintaining coherent motion toward distant destinations determined by cosmic web architecture. Rest knowing that cosmic forces operate with reliability exceeding any human institution, following mathematical principles discovered through scientific investigation, yet operating according to natural laws that preceded conscious observation by billions of years, creating trustworthy cosmic currents that will continue carrying our galactic neighborhood through immense heaven, regardless of terrestrial events or human activities, connecting present moments with infinite cosmic futures guided by gravitational certainties that transcend all temporal limitations.